In this lesson of our course, we're going to go over differentiation and integration of the hyperbolic functions. Now, some of you may not have seen the hyperbolic functions before, and if that's the case, that's fine. It's just going to be some formulas that you need to follow. And some of you may have seen this, so this will be a review. But this function right here, it looks like sine with an h added on the end of it. That's called hyperbolic sine. And this one here is cosine with an h added on the end of it, and that's hyperbolic cosine. Hyperbolic sine is defined by e to the x minus e to the negative x, all divided by 2, and hyperbolic cosine is defined by e to the x plus e to the negative x all over 2. Now, there are 4 other hyperbolic functions, and it's similar to what you learned in trig. We have hyperbolic tangent, hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant. These functions are all based on these formulas right here. So, for example, hyperbolic tangent is just as you want to think of it in terms of your trig functions. When we think about tangent, we think about sine over cosine. So when we talk about hyperbolic tangent, our function would be defined as hyperbolic sine over hyperbolic cosine. So I would take this and divide it by this. Hyperbolic cotangent would just be the reciprocal of that, where I would take hyperbolic cosine and divide by hyperbolic sine. Hyperbolic secant would be the reciprocal of hyperbolic cosine, and hyperbolic cosecant would be the reciprocal of hyperbolic sine. So everything is based on these 2 equations here. Now, if you haven't seen these graphs before, this is what they look like here. They're all labeled here so you can see what they look like. Now, when you take the derivative of a hyperbolic function, here's the table here of how to follow the rules. So hyperbolic sine, if I take the derivative of hyperbolic sine, I'm going to get hyperbolic cosine. Okay, the derivative of hyperbolic cosine is hyperbolic sine. Okay, so you just want to follow this chart here. Now, I want to show you one of the proofs because the rest of them pretty much follow the same pattern here. I'm going to show you how we get the derivative of hyperbolic sine, and then the rest of them pretty much follow that same pattern. So I'm going to take the derivative of hyperbolic sine. Now, hyperbolic sine function is defined by e to the x minus e to the negative x all over 2. So I'm going to rewrite hyperbolic sine as this definition here. Now, I'm going to clean this up a little bit to make it easier. So I'm going to split this up into 2 functions so I don't have to do that. So I'm going to rewrite this as 1/2 e to the x minus 1/2 e to the negative x. Now, when I take the derivative, I get 1/2 e to the x. And then when I take the derivative of this, I end up getting a plus here because I have to take the derivative of negative x using the chain rule. So when I take this negative times that negative, I end up with a positive. So I have minus 1/2 e to the negative x, and then I multiply using the chain rule. I multiply by -1, which changes that to a plus. And then if we rewrite that as e to the x plus e to the negative x all over 2, that is the same thing as hyperbolic cosine. Now, all of these can be derived the same way. I would take, since hyperbolic tangent is hyperbolic sine divided by hyperbolic cosine, I would take this divided by this, simplify it, and then take the derivative of that. And I just go through the same idea for all of these. I define all of these functions based on the 2 identities above, and then take the derivative. Then working backwards, here's your integration rules for hyperbolic functions. It's just working backwards. So let's look at our first example. Here it says, find the derivative of hyperbolic sine of x squared. Well, we're going to use the chain rule with hyperbolic functions. The derivative of hyperbolic sine is hyperbolic cosine. So I'm going to have hyperbolic cosine with this x squared, but using the chain rule, I have to multiply it by the derivative of what's inside, which would be 2x. For this one here, this is using the power rule and the chain rule. I have an inner function here. This is the power rule. I have something squared. So I'm going to bring the 2 down in front. That's here. Decrease this power by 1. The inside stays the same, but then I have to multiply it by the derivative of the inside. And we know that the derivative of hyperbolic cosine is hyperbolic sine. So now let's look at integrals involving hyperbolic functions. For this one here, I'm going to use u substitution. I'm going to set u equal to x squared. That means when I take the derivative of u, I get du is equal to 2x dx. And then because I want to, since I've already replaced this with u, I want to replace the x in the dx with something in terms of u. So I want to isolate x dx to see what I need to substitute it with. So I'm going to divide both sides by 2. So I get x dx is equal to 1/2 du. So now I can rewrite my integral as hyperbolic cosine u du. When I integrate that using the rules above, I get hyperbolic function for sine of u plus our constant. And of course, I need to go back and resubstitute my u for x squared. For this one here, I'm going to rewrite hyperbolic tangent for hyperbolic sine over hyperbolic cosine. That way I can let u be hyperbolic cosine, and I can do a u substitution. I get the du is hyperbolic sine dx. And that way I can replace this with u. Sine, or hyperbolic sine dx can be replaced with du. Now I know what this is. This integral of 1 over u du is the natural log of u plus our constant. So when I go back and resubstitute, I get the natural log of hyperbolic cosine x plus my constant. All right, now we're going to go over the integration rules and the derivatives of inverse hyperbolic functions. Now, for most of you, I'm assuming that you may not have seen this before, so I put the graphs in the notes here so you can see what they look like. And then I put the domain and range for the inverse functions here. Just like cosine and sine, or any other function that is not one-to-one, we have to restrict the domain so that when we find the inverse itself is a function. So keep that in mind when you're looking at the domain and range of the inverse hyperbolic functions. If we scroll down further, I put all the rules in here for the derivatives of the hyperbolic functions. Then as we scroll down further, I have the rules of integration for the hyperbolic functions, for the inverse hyperbolic functions, I should say. And that's all listed there. So make sure you keep that handy while we're working the next examples. So let's go through examples of derivatives of the inverse hyperbolic functions. So for this one here, we want to take the derivative of the inverse hyperbolic sine function of x divided by 3. So we're going to need to use the chain rule. So for the inverse hyperbolic function, the derivative will be 1 over the square root of 1 plus whatever that inner function is, that's here, squared, And then using the chain rule, I have to multiply by the derivative of what's inside, which would be 1/3. Now, when I clean this up, I actually wasn't very careful when I wrote this. This, if you notice, parentheses should actually be here. So the 2 is outside because I don't want to just square the x. I want to square the x and the 3. So I should have been more careful with my parentheses. But when I square x over 3, you get x squared over 9. And then when I multiply it by 1/3, my final function after I clean it up a little bit is 1 over 3 times the square root of 1 plus x squared over 9. Now for this derivative here, we're going to have to use the power rule and the chain rule. I have the power rule here because I have an inner function that's being squared. So I'm going to take that 2, I'm going to bring it down in front, that's here, and then I decrease this power by 1. The inner function stays the same, but then I have to multiply it by the derivative of the inner function. So if you look at the chart above, the derivative of inverse hyperbolic tangent is 1 over 1 minus x squared. So that's what I need to multiply by. Okay, now let's do a couple examples of integration with inverse hyperbolic functions. So I have this integral right here. I have dx over the square root of 4x squared minus 1. The closest thing I can get to when I look at my chart is this here, which is hyperbolic inverse cosine. So I'm going to make a u substitution to try to rearrange it so that I can get it to look like that integral. So I'm going to let u be equal to 2x. So that way when I square the u, I get 4x squared. So I'm going to replace this 4x squared with u squared. Now when I take the derivative of u, I get 2 dx. And I want to replace that dx, so I'm going to isolate the dx, and I get 1/2 du. So this is where the 1/2 is coming from. I replace dx with 1/2 du. Then underneath I have the square root of u squared minus u. Now I can use the integration rule that's above. So I have the 1/2 here. The integral of this is inverse hyperbolic cosine of u. And then, of course, I want to add in my constant. And then I have to go back in and substitute my u's for my x's. So my final answer is going to be 1/2 hyperbolic cosine inverse of 2x plus my constant. Now this next one here is a little bit tricky. I had to do a little bit of finagling to get this to work. So I tried a couple things, but this is what ended up working. So I let u be 3x. So that means du is equal to 3x, which means x, if I divide both sides by 3, is 1/3 u. So I started doing my substitution. So I have 2 times x here. So I have 2 times x, and since x is 1/3 u, I put that here, 2 times x. I'm replacing dx. When I use this here, and I divide both sides by 3, I get that dx is 1/3 du. So I have 1/3 du up here. Now, I got rid of the 1/3, the same on the top and the bottom. I just divided that out. So what I was left with is this 1/2 du over u times the square root of 1 minus u squared. That, if you look at the rule up top, above here, you see that that's inverse hyperbolic secant. And I have this negative in front here because that's part of the formula. This 1/2 is carried from here. Let me scroll up to show you. So that's this right here. I'm using this one. So I have negative. That's part of the formula. The 1/2 was just a constant that I had out in front. So I have negative 1/2 hyperbolic secant inverse, and then absolute value plus the constant c. And then I did a substitution and plugged 3x back in for u. So here's my final answer right here. Okay, last example. It says, assume a hanging cable has the shape 10 hyperbolic cosine of x over 10 on the interval from negative 15 to 15, where x is measured in feet. We want to determine the length of the cable. So we learned this in a previous section, the arc length of a curve on a certain interval. So we're going to use that formula. Here was the formula for our arc length. I believe it was section 2.4, but I can't remember for sure. So here's our formula for arc length, what we're going to use. We're going from negative 15 to 15. And so I need to find the derivative and square it so I can plug it in here. So f of x is 10 hyperbolic cosine of x over 10. When I take the derivative, I get 10 times hyperbolic sine of x over 10 using the chain rule times the derivative of what's inside, which is 1/10. So these 10s are going to disappear because I can take 10 over 10, which is 1. So I get that the derivative is hyperbolic sine of x over 10. Then I need to square that derivative. So I get, whoops, I forgot my 2 here. This should be a 2 here for squared. But when I square that, I get hyperbolic sine squared of x over 10. And that's what's going to go in here. We have an identity. 1 plus hyperbolic sine squared is equal to hyperbolic cosine squared. So I'm going to substitute this with hyperbolic cosine squared. And when I put the hyperbolic cosine squared under here, the squared and the square root undo each other. So I'm just left with the integral from negative 15 to 15 of hyperbolic cosine x over 10. Now I'm going to do a u substitution. I'm going to let u be x over 10. So that when I do my substitution, I'm going to get that 10 du is equal to dx. So I'm going to replace dx with 10 du. So I pull the constant out here in front. Here's my du. Now, because this is a definite integral, I have to change my limits as well so that they're in terms of u rather than x. So if I take negative 15 and 15 and plug it in here for x, I'm going to get that my values of u are negative 1.5 and 1.5. When I do this integration, I get that I have 10 hyperbolic sine, and we're going to evaluate it from negative 1.5 to 1.5. And when we punch that in on the calculator, we're going to get 42.59 feet. Now, I'm aware that some of you may not know how to access hyperbolic functions on your calculator, so I'm going to show you how to do that. Okay, so we have a bunch of functions on our keypad, but hyperbolic functions are not on the keypad. So we're going to have to go directly to the catalog for that. And the catalog is where every single command and function is located. Okay, so to access the catalog, if you notice above your 0 button, mine's in blue right here, it says catalog. So you want to make sure you push the corresponding button that matches that color for catalog to access the catalog. Since my catalog's in blue, I'm going to hit the blue button here, and then I'm going to hit 0, and my catalog is going to show up. Everything is listed in alphabetical order. So if I want to find hyperbolic sine h, I'm going to scroll down to the s's, and then I'm going to find sine h. Okay, so here it is right here, sine h, and then here's hyperbolic sine inverse right here. I'm going to choose hyperbolic sine, hit enter, and I'm going to put in 1.5. That gives me this value. Then I'm going to do it again for negative 1.5, and that's going to give me this value. Then I'm going to take this minus this and then multiply it by 10 because we have this 10 out here. And that should give me the 42.59 feet. So any of the hyperbolic functions you want to access in your catalog, whether it's hyperbolic inverse or one of the regular hyperbolic functions. So you're going to hit your second button, which should correspond to the color of the catalog. Hit second and then 0, and all your commands will come up there.